biomedical data for stress estimation, and Xuping from Major University is talking. I would like to move to the introduction. Here, recently, the quantitative analysis of the sleep quality and the stress estimation has been important social issue. And there are so many conventional works here to judge the sleep quality. It is mainly focused on the subjective questionnaire. And the stress is estimated by spectral analysis of the ECG here. But there is a problem here that the measurement is quite difficult during the sleep since the restrictions on the respiration rate and body motion. And furthermore, most of the sleep depth transition is presumed by the heart rate. However, the problem here is that the relation between heart rate and sleep quality during sleep is not clarified. So what we want to do is just to fix these problems. So the research purpose is like that. First, we would like to collect heart rate and the sleep depths while wearable IoT equipment to estimate the stress during sleep using a spectral analysis. And when we do the stress estimated, we just collect two data. One is the heart rate variability, the other one is the sleep depth. And we also want to calculate the correlation analysis between heart rate and sleep depth here. Furthermore, there isn't any work in the conventional works to consider privacy preserving issue. So what we want to do is just to encrypt the data, to apply the encryption to distributed data for analysis considering privacy preserving. So now I would like to show the risk towards privacy bioinformation for stress estimation here. So we have a scenario like this. In nowadays of Japan, the suicide problem has been, because of our work, has been focused. For example, there are two density and NHK problems. It's been a very serious social problem. So in the case here that maybe the labor association would like to identify the stress index based on overtime working hours of companies as a reference to prevent suicide. So they may require for information of employees to the companies. So the companies will supply the employees information to the labor association, for example, the age, the gender, the work hours, including the personal information here. But there's another problem here. Maybe there were some hacker or insider cracker here in the labor association. So there must be maybe some malicious third parties here. For example, the insider will send the information and to the third party and sell it. So it may cause some abuse or something. So what we want to do is just to prevent the third parties here. So what we want to do is, it is the figure that we would like to supply the solution. We have considered two providers who will provide the distributed data here. The second one is we would like to do the encryption analysis here. So there are two providers here. The upper one is the hospitals or research institutes. They just supply the heart rate and sleep depth of the personal data, and they would like to apply the spectral analysis to it to get the low frequency density and high frequency density. And these two stress indexes are used to calculate the stress here, for example, to get this value. But however, as we would like to consider privacy preserving, they will not provide the raw data. They will encrypt all the data into this part and then supply encrypted data and a shell key for the decryption to the provider B. And the provider B just collect the overtime working hours instead of the personal information. So finally, according to this distributed data, we would like to do the analysis and to do a calculation here with this over, for example, as this overtime, the stress will be over 2, so it will be very dangerous like this, so they'll control the overtime hours, something a scenario like this. So this is a summary of the problem and our solution. The problem is that data is quite difficult to be collected, and the correlationship between sleep and depth is not cleared. and none of the work considered privacy-preserving issue. So our solution is just to solve these three problems. One is to collect the sleep depth and the sleep and heart rate with the IoT device every 5 minutes automatically. And the second, to apply the spectral analysis to time sequence data to evaluate the stress during sleep and to calculate the correlation between heart rate and sleep depth. And finally, to apply the privacy-preserving linear regression to dummy data as a primary work here. So now I would like to show a data here. We just have devices, two devices. One is like this, it's retrievable for the sleep depth, and the other one is here for verify is for heart rate here. And we got data here, and for the sleep depth, there are 4 stadiums here: wake, REM, light, and deep sleep. And it will be detailed into 1 minute. And it also collected one heart rate here. And there is only one participant, it's me. And we collected over 5,000 samples here. And this is the data like this. We have an average of 70. And this is the output of the real data. The first one is the heart rate here, and the bottom one is the sleep depth here. The gray zone means the days that when we are asleep, and the blue zone means the daytime, so when we are awake. And here, for the sleep depth, there are 4 stages here, 4 stages here. And if we have 4, it means that we are awake during sleep. And when we have 1, it means that we have the deep sleep. So it's better to have lower value here. So we can understand there was some danger signs here is about 135. I asked my doctor, and she told me maybe I'm just a dream or nightmare, maybe. Okay, move to the next page. If we would like to estimate the stress, we have to calculate the analysis of the spectral. We use the power spectral density here, PSD. The PSD is used to show the strength of the variation in frequency domain instead of time domain. And we would like to analyze the specific frequency range where the peak power located. And it is calculated by this volume here. By this one, we will get spectral power here. And the power spectral is the FFT, the Fourier transform result of the autocorrelation, according to this thing here. And we have the autocorrelation here. It is calculated by this data. It is the relationship between the heart rate in time t and in time tau ahead. So we can calculate it out the spectral power here in this formula. Let's move to the next page. It is the formula that's how we calculate the stress index. We have a lower frequency value here and high frequency value here. It's located in different domain here. And this is the ratio index here. We can see if we have lower LF and higher HF, it will be better. Your stress will be lower. Okay. So this is a stress index. So we can see if we have data lower than 0.8, this means indicates a relaxing status. And if the value is bigger than 2, it indicates it's very stressful status here. And then I would like to move to the next page. This is the transition of the heart rate here with over 1 month's date here. We can understand the blue one is just the date after 1 hour before sleep, and the red one is just the days of the average date during sleep. We can understand the average heart rate during sleep is lower. It is lower than 1 hour before we sleep. So maybe it's a possibility that the heart rate 1 hour before sleep is affected by the activities during daytime. Okay. And this is a transition of the index during sleep about the low frequency domain and high frequency domain. And we can understand that it's better to have lower value in LF and higher value in HF. So we can see on 18th June, we can understand we have better value here. So maybe on this day is a very relaxing day. And on last day, I just attended a violin piano concert, and it's a little bit stressful in other days, unfortunately. And this is the transition of the stress index. We can understand that in the previous page, we could understand only days of relaxing days, so the stress index is very low here. And on the other day, the data has been over 3.5 is a little bit stressful. So only day is a little bit strange because the heart rate, the index, stress index of the heart rate and sleep depths are quite different. So we want to say which one is the correct date. Okay, and we will do it later. And this is a comparison of the PSD of heart rate and sleep depths during sleep. On the left side is from the 8th of June, and on right side is a relaxing day on the 6th of June 18. And we can understand the red zone is indicating the date low frequency, and the green zone just locating the high frequency. So as we have said, if we have better high frequency date here, it means relaxing. So on the left side is a little bit stressful because of the coefficients are located in low frequency domain. And we could see on the right side it is a little bit relaxing here. So, and by analyzing the date here, we can understand the date here, they are quite different, 0, 6, and 3. This is for heart rate. And on the right side, it is for a sleep depth. We can understand both of the dates are 0.4. So I just suppose the sleep depth just indicated correctly for the stress estimation. Sorry. And I would like to give some supportive data here to check the result. Here, this is a relaxing day and this is a stressful day. And we would like to see that the average heart rate is lower here. And we have longer time for the deep sleep here. And we also have a shorter time for awake. So I suppose this data is very supportive for the information in last page. So, I would like to show you the real data of have a comparison between these 2 days. On the left side is a stressful day, and on the right side is a very relaxing day. And we could understand the heart rate just stay lower and stable when we are relaxing. And we have longer time to have deep sleep when we are relaxing. So it is another supportive data for the results as I have shown you. And now I would like to calculate the correlation between heart rate and sleep depth. And actually, we have calculated the data here and on different days. And if the data is closing to 1, we will say there is a strong correlation. But unfortunately, the data is very small. So we just say only 2 days they have a weak correlation between heart rate and sleep depth, and there are seldom correlation results on the other days. And the second, there is because there is a paper here indicating that listen to music helps you relaxing. So I just check the daytime activity and the sleep quality. And this is comparison between heart rate and sleep during daytime and night, and we can understand that there is seldom correlation between the days because the value is very small here. So in the conventional work, they just want to presume the sleep depth according to heart rate is not correct. And now I would like to move to the discussion about privacy preserving here. The current problem is, as I have shown you in the scenario, is that if the labor just collected the raw data, they just abuse it or sell it to the third party. So in order to prevent this, we would like to prevent the malicious insiders to get the information and to calculate the data in a encryption way. in an encrypted way. So our aim is to firstly to encrypt the date and to calculate date, to reuse the date, to make it date computable. And we also would like to collect distributed data processing, since different providers without disclosure to data to each other. So this is what we want to do. We applied the encrypted linear regression here to show the correlation between variables like we have y, x, and alpha, beta here. So this time we have the y as the heart rate, and we have x as the sleep depth, and we have x2 as the overtime working hour. We also have the intercept alpha here and the coefficient beta here, because we have two variables here. The alpha and beta was calculated by this formula, and this because the data are separated by two parties, so there must be some protocol to show the date here. So there are two parties. The party A will do the encryption and decryption, and they will on date of the Y, and they will have the key of the private key here. The party B will calculate the linear regression here, and lay on the date X, and have the private key here. So there is a simulation of the protocol here. The party A will firstly generate the key, and then send the key to party B. And party B will receive the public key here, and party A will encrypt the Y value here to get the encrypted value here, and send it to B. And B will compute information according to the date here, and the result is also encrypted value here. And then we'll send this date into party A again. And party A will encrypt it to get original date, and to finally to obtain the alpha and beta here. And the encryption condition is like this. The data set, we have two dates. One is the heart rate and sleep depth is a real date. And over working hours, we cannot collect it, and this is a dummy date, which has been calculated according to this formula. And the date site is set to be different date site to check the computational time. And the environment is like this. And the encryption calculation is implemented by Java, and the raw date is calculated by R here. And this is the result of the computable time here. We can understand that when the data is getting larger, we have to use more computation time here. And here we have alpha, beta, and beta 1 and beta 2. And alpha just stay very steady. They are similar. And for the beta, it indicates to just have a variable, change a lot. So there are two possible reasons here. One is the working hour is a dummy date because it is not a real date here for the experiment. And the second one is because we just use the average heart rate as 17. So when I have a heart rate of 15 or 19, it's unfair to calculate. So maybe the data is not good, maybe. And this is the comparison between encryption and raw date here. On the red zone, we have it is implemented by Java, and the result of the encrypt is estimation. And on the right side is estimation date calculated by raw date here with the alpha, sleep depth, and hours here. We can understand the results are very similar together. So even though we use the encrypted dates, the result is close to the original one. So we would like to say this method is valid and precise as well as privacy preserved. So this is a conclusion. So the achievement of this work is that this work collected data during sleep, and the second we applied the analysis of spectral to estimate the stress, and we also applied the encrypted linear regression, and the result is calculated to be effective. So the future works is like we would like to apply the privacy preserving to prediction to see some danger or status or something. And we also would like to improve sleeping quality by analyzing the environment, the center date, and to do some subjective evaluation on sleep quality.